Hello, everyone. Dear authors and invited guests, it is my great pleasure to welcome you to the 6th International Congress on Information and Communication Technology through Zoom on behalf of ICICT 2021 and Global Knowledge Research Foundation. As every one of us is passing through these unseen circumstances due to COVID-19, we wish everyone and their families a safe time, and we all will together pass this soon. Further, with immense happiness, I would like to share that we have received an overwhelming response this year from across 90 countries, where 1,150 papers were received and 350 papers were accepted, contributing to the success of this conference, and the papers would be published in 4 volumes this year. We are thankful of all our guests present on this platform to join us digitally for the conference in these unpredictable times and make this conference more fruitful in terms of technical knowledge, and hope you will enjoy the 2 days of knowledgeable and interactive sessions. I would like to welcome you to the technical session 2E and further introduce the session chair, Dr. Shamim Kaiser, who is currently working as a professor at the Institute of Information Technology of Jahangirnagar University, Bangladesh. He is an associate editor of the Cognitive Computation and IEEE Access Journal, guest editor of Britain Informatics Journal, IGACI, and Cognitive Computation Journal. Dr. Kaiser is a live member of Bangladesh Electronic Society, Bangladesh Physical Society. He is also a senior member of IEEE USA and IEICE Japan, and active volunteer of the IEEE Bangladesh section. He is the founding chapter chair of the IEEE Bangladesh section Computer Society chapter. Okay, so we will start with the presentations. To start with, Dr. Hannes Marine will present implementation-free forensic watermaking for adaptive streaming with AB watermaking. Dr. Hannes, the floor is yours.
All right, I'm going to share my screen.
Okay.
Can you see it?
Yes.
All right, perfect. So hello, everybody. My name is Hannes Marine from Ghent University in Belgium. And today I will present to you my work about forensic watermarking. And rather than focusing on the long and complicated title, I would simply like to say that my presentation is about Pirates of the Caribbean, and more specifically, how to securely distribute movies such as Pirates of the Caribbean. And we wanted to do this for video distributors such as Netflix and Disney Plus that have to send the video to a huge amount of users. So if you think about it, how are videos distributed to users that are paying for their platform? For example, to Will, Elizabeth, and Jack. So we can send the video to Will, can send it to Elizabeth and to Jack. But now if one of these users decides to do something illegally and upload it to the Pirate Bay, then we don't know who actually did this. So we don't know who the pirate is. And that's why we want to do it securely. So we want to add a watermark in the video, for example, a number in the visual text in the video. For example, 1 means Will, 2 means Elizabeth, and 3 means Jack. And then if somebody decides to leak this video on the Pirate Bay, we can simply read this number, and we know that in this case, Jack has leaked the video. Now, of course, Jack would be a very bad pirate if he didn't do anything about this obvious watermark in the video. So we can simply delete it, making him unidentifiable. And so we don't know who is the pirate anymore. And you may think that this visual watermark is a very bad way of watermarking, and you are correct, but it was actually used in practice. Here is an introduction of Game of Thrones, the famous TV series. And a couple of years ago, you could download this video on the Pirate Bay. Before the video was actually visible on HBO, the legal platform, you could already illegally download it. And we can see a blurred watermark in the lower left corner. So it said something such as "send to Jack Sparrow," but this pirate simply deleted this watermark by blurring it. So we want to do a better job in my work, but let's first go over some requirements for good watermarks. So first, the watermark should not be visible, as we just said. We shouldn't be able to see the watermark, and we shouldn't be able to delete the watermark. So the watermark should not be weak. Instead, the watermark should be invisible. We shouldn't even know that it's there. And this also means that it shouldn't decrease the video quality. We don't like to watch a pixelated video, and we also don't want to increase the video bitrate. So we don't suddenly want to receive gigabytes of data more when we watch a video through Netflix. So not only should the watermark be invisible, it should still be there. Like, we don't see it, but it should be there, and it should be robust. This means that it should survive attacks by pirates. Even if pirates try to delete the watermark, they shouldn't be able to do that very easily, so that we can still detect it, even when they, for example, lower the quality of the video. Also, the watermark should be scalable. For platforms such as Netflix, it's very important that the user can be sent to, the video can be sent to thousands of users at the same time. So this should be possible in this watermarking strategy. And also, it should be easy to use. It should be easy to implement for the video distributors, so that they don't need a whole new team to do watermarking only. So now on to the proposed method that I'm proposing in the paper that I submitted to this conference. So let's first go over some video compression basics. When we have an uncompressed video, it's, for example, 1 gigabyte per second in size of raw data. So we typically compress this video. And the thing is that we don't really see much difference between the uncompressed and compressed video, even though we went from 1 gigabyte per second to 100 kilobyte per second. But even though we don't see a difference, there are actually many differences in these videos. There are many compression artifacts that were automatically created by the video encoder that compressed the video. And the video encoder works in a way that he removes the most imperceptible information first, so that we as humans don't really see the mistakes that it introduced. And now the thing with my method is that I compress it slightly differently. So for example, to 99 kilobyte per second rather than 100 kilobyte per second. And we still have some compression artifacts, just as in the other one. But the thing is that these compression artifacts from 99 kilobytes per second are different than those of 100 kilobyte per second. So if I go back and forth, I hope that it's visible through Zoom as well, that you can see that there are some small differences. And these differences, which are visualized here, these consist of the watermark. So if we go over this in summary, we have an uncompressed video and we can compress this to, for example, 100 kilobyte per second, and we have some compression artifacts. Now we can also compress this to 99 kilobyte per second, and again, we have some compression artifacts. Now the differences between these two videos, this is actually the watermark that is introduced. And these are consisting of invisible compression artifacts. So this is great because we want the watermark to be invisible. And so how do we do this? Well, typically when we do compression, we simply give the uncompressed video as input of a video encoder together with the target bitrate, and we get an compressed video as output that is approximately the same as the target bitrate that we gave as an extra input. Now, in watermarked video compression, we do this instead of 100 kilobyte, 100 minus 1, where 1 is the watermark ID. And this is how we can create several unique watermarked videos that we can then send to the users. So this means that the watermark is easy to use because we only needed a video encoder that video distributors are using anyway, because they are sending compressed videos and not uncompressed videos. So now, what if we find one of these videos on the Pirate Bay? How do we know who leaked the video? And it could be that he performed an attack on the video, for example, by lowering the quality and hoping to remove these unique compression artifacts that I use as a representation of the watermark. So how I do this? Well, we have a pirated video and, for example, 20 watermarked videos that we distributed to the users. Now we can simply compare this pirated video to these 20 videos, and we can plot these distances on a graph. And we can see in this example that one is clearly less far from the pirated video than the others. And this is watermark number 10. So we can detect this as the watermark. And this is some sort of outlier detection that I'm not going to go into the details of. So now on to the results of this method. First, how invisible is it? How well do we need to look in the video to see if there are actually any differences from the watermark? So in the state of the art, we typically need about 1 to 8% of BD rate, which means that for reaching the same quality, we need about 1 to 8% more bits than we need for an unwatermarked video. While in the proposed method, we need about 0% more. So actually there is no overhead. In some cases, it's a little bit more than 0, and in other cases, it's a bit less than 0. So on average, it's about 0%. So this means that the watermark is in fact invisible, and it's not decreasing the video quality, and it's not increasing the video file size on average. So now the second result that we want to analyze is how robust is it? Can we still find a watermark after we perform detects? How well do we need to look in the video then? Well, without going into too many details, because time is limited, when we recompress the video to a much lower quality, as you could see here, you may think that, we can't see these invisible compression artifacts from the first watermarking step anymore. But in fact, we actually can. While the state of the art is often unable to be robust against such an attack, this method can still do it. This means the watermark is robust. Now, onto a last problem is that the watermark is, it's not scalable. If we have 200 users, then we need to send a video of 1 kilobyte per second up to a video of 200 kilobyte per second. So this is a huge difference, and we can't do this. So a scalable solution is A/B watermarking. And instead of having 200 versions, we have only 2 versions, an A and a B version. And by combining these versions in A/B watermarking, we can create any watermark ID that we want. For example, 1993. This is a pattern of bit ones and zeros of bits. And this means a pattern of A's and B's. And by combining these, in this pattern, we can represent using only A and B, we can make watermark ID 1993, for example. And each of these A's and B's is a small segment of a few seconds, for example, 10 seconds. So with less than 2 minutes of video, we can actually represent watermarks with so many bits. And on average, this is 100 kilobyte per second, which makes it scalable. So this is also very easy to integrate in adaptive streaming that Netflix and Disney Plus are already using. So in adaptive streaming, if we have an uncompressed video, we can send it at 4K to a big television, but to smaller televisions, we can send it at 1080p, and to tablets to in 720p, and for users with different network connections, we can send other bit rates. And if somebody's network's connection becomes worse or better, we can change the video that he's receiving depending on his network conditions. So in adaptive streaming, we have already 5 versions of the same video compressed at different bit rates. And now in A/B watermarking, we simply need, instead of 5, we need to have 10 of them. For each of those versions, we have an A and a B version. So this means that A/B watermarking is very easy to integrate in adaptive streaming that Netflix and Disney Plus are already using, and other video distributors as well. So this means that the watermark...
Sorry, you still have 2 minutes.
All right, I'm basically finished. So this means that the watermark is scalable. So in conclusion, what have I done? I created a watermark that is invisible because the watermark consists of invisible compression artifacts that are present in videos anyway, because we compress them. The watermark is robust because it can survive severe attacks that lower the quality severely. The watermark is scalable if we combine it with A/B watermarking. So we only need to create 2 watermarked versions to be able to send it to thousands or even millions of users. Or of course we can send, we can create 10 different versions. So we need to have less minutes of video to detect the watermark. And the watermark is easy to use because all we need is a normal video encoder that we need anyway. And with A/B watermarking is also easy to integrate in adaptive streaming, which is already being used as well. So in conclusion, pirates beware because we're coming to catch you. So yeah, this was my presentation. If you have any questions, you can ask them now, or you can send me an email, or please also send me a LinkedIn connection request, and I'll be happy to answer them.
Thank you. Thank you for the great presentation. Any questions? Okay, now we move on to Dr. Ruby Lee with a study on the generalized normalization transformation activation function in deep learning based image compression. Dr. Ruby, the floor is yours.
Can you hear me?
Yes.
Okay, so hi everyone, I'm Qiang Duan. I replace Dr. Ray Li to make this presentation. And
I'm sorry for the interruption. So are you presenting on behalf of Bruli?
Yeah. He's my colleague and he has some personal issue.
Okay, yeah, no problem. Please continue.
Okay. I'm from Technology Center of Inspire Group, Shandong, China. I'm glad to share our work here. So in this paper, we conduct several experiments to compare the generalized normalization transformation and other commonly used activation functions, as well as their variation. Then we evaluate the performance of some combination of these activation functions and JDN itself. So there are the different processes between the traditional signal-based compression and learning-based compression. In signal processing-based image compression, for example, the JPEG standard, it consists of converting color space using signal transformation, filtering the frequency, quantizing and using entropy coding, etc. In learning-based image compression, the fundamental network structure is a generative model based on the autoencoder structure. So each layer is followed by JDN or inverse JDN respectively. And the encoder is able to reduce the dimensionality of input images through the convolution operation with the stride larger than 1. Then after encoding, the original image information is initially compressed. Then the compressed data is sent to the bottleneck layer. The bottleneck layer between encoder and decoder is responsible for the quantization and entropy coding. The quantization method is a uniform scalar quantization, and the entropy coding used here is arithmetic entropy coding. We adapt the network structure slightly, that we used 5x5 convolutional layers to replace the original 9x9 convolutional layers, and positioning them at the first layer of encoder part and the last layer of decoder, respectively. Due to the further decomposition, will introduce more layers and result in a rather deep network. We didn't use the 3x3 convolutional layers in original paper. So with the 5x5 convolutional layer with 128 kernel in each layer and stride 2, the encoder downsamples the size of image to 1 to the 16th with 128 channels. So there are the main equations used in the network, and I don't intend to explain the details. But in brief, the model jointly optimizes the bit rate, distortion, and normalization factor, the lambda of JDN. So as mentioned before, the quantization method is uniform scalar quantization. So there are the 4 activation functions used in our study. The first one is ReLU. It is commonly used in general convolutional networks, which solves the gradient vanishing problem, but introducing the dead ReLU problem. And then the leaky ReLU solves the dead ReLU problem. The dead ReLU problem, and but it has a limited improvement compared to the original ReLU. The third CELU solves the gradient exploration and introduce self-normalization features. The JELU has good performance in BERT, so we are curious about its performance in on the computer vision tasks. So in our experiments, we firstly evaluate the performance of JDN and regard it as a baseline. Second, we try to compare different activation functions to the baseline. Finally, we select 2 of them to append to JDN to verify whether the combination of general activation functions and JDN surpass a single JDN. We examine the model behavior when applied to the 6 different scenes, including an animal, crowded scenes, a monitor captured images, the outdoor scenes, landscape, and person. So the metrics concentrate on the 2 aspects, the bit rate and the distortion. For the distortion, we use the objective evaluation matrix PSNR and a perception-based model SSIM. The PSNR estimates the absolute error of reconstructed images, and the SSIM considers images degradation as the perceived change in structure information. And for the bit rate, we calculate the bit rate that is a fraction of total bits and the total number of pixels, where the total bits is counted from the number of binary serialization encoding characters. So here is our experiment's result. The above table shows that the JDN has a remarkable performance on encoding bit rate. As for the remaining activation functions, the CELU plus JDN has a close performance to JDN. And the below figures illustrate that the SSIM and the PSNR value. Their horizontal axis indicate the 4 BPP values derived from different lambda values. And generally, with the bit rate increasing, the SSIM and PSNR metrics are also increasing, but the growth shown here is slowing down. In this SSIM part, JDN shows the best performance over all scenes comparing to the rest activation functions. And in PSNR part, JDN plus CELU functions has better reconstructing quality than JDN over most scenes, and the separation is distinguishable. However, the better performance is under the cost of extra bit rate, indicating by the above result. So in conclusion, the experimental results suggest that the JDN is a good choice in deep learning-based image compression, since it has a good balance of bit rate and distortion. However, using JDN plus SALU functions has a potential ability to achieve better performance on image reconstruction. So in the future work, we think we can do more benchmark to verify the model behaviors, such as the standard image compression dataset called Codex dataset. And we think exploring the combination of SALU and JDNs by using the Lacan norm initialization method is a good choice because it is suggested from the original paper. And then explore more autoencoder structures, such as variational autoencoders. Made the state-of-the-art work can help to improve the performance of image compression. So that's all. Thanks.
Okay, thank you. Thank you for your presentation. Any questions? Okay, then we will move on to Dr. Pablo Soto Quiroz, presenting a fast algorithm for image deconvolution based on a rank constraint inverse matrix approximation problem. Dr. Pablo, the floor is yours.
Okay, thank you so much. Okay, you can see the presentation?
Yes, we can.
Okay, thank you. My name is Pablo Soto. I was working with other two colleagues, Juan José Fallas Mongen and Jeffrey Chavarria from Costa Rica Institute of Technology, and the presentation is a fast algorithm for image deconvolution based on a rank constraint inverse matrix approximation problem. Well, I start with the motivation. Image deconvolution is an image processing technique designed to remove blur, contrast, and resolution. If capital X represents an image, then the mathematical model in image deconvolution is given by this formula. X is a vectorized version of capital X. A is a matrix that models the forward process. Eta is an additive noise, and C is a vectorized version of the noise image, capital C. Given C, the goal of the inverse problem is to reconstruct image X. To solve this problem, we use training data. Here we have two sets of training data. The first one represents the image without noise, and the second one represents the image with noise. And the problem is try to find the optimal matrix F that solves this problem here. This matrix F tries to clean the image with noise, and we want to have a good approximation of the image without noise X. This problem can be reformulated using the Frobenius norm. And finally, we work with this problem. Here we have two matrices C and X, capital C and capital X, and are created, both matrices are created using the training data. When we obtain the solution of this problem, the optimal matrix F, we just do a matrix vector multiplication to obtain the estimation of the original image given by this formula. The solution of, well, this problem is so-called the rank constraint inverse matrix approximation problem, and there is a disadvantage with the solution of this problem, because the solution uses the singular value decomposition to estimate the pseudo-inverse and the low rank approximation, and it is impractical in the case of large matrices. In this work, we propose a new and efficient method to compute a solution of the RCIMA problem, and this algorithm have to use two fast algorithms to approximate the pseudo-inverse and the low rank matrix approximation. The pseudo-inverse, the method is based on a tensor product of two vectors and the Tikhonov regularization. And to estimate the low rank approximation, we use a method that uses the bilateral random projection and its power scheme modification. The new method reduces the execution time to compute the solution of the problem P1, and the most important, preserve the same accuracy of the classical method. Okay, the original method, the original algorithm to solve this problem is given in this algorithm. We need to create the matrices capital X and capital C using the training data. We compute the SVD of matrix C, and we just need to use the right singular vectors. And the first K, where K is the rank of C, we create the matrix P, and with this matrix P, we obtain the low rank approximation of the matrix P, and with this formula, we compute the optimal matrix F. The problem here is we use the SVD and we use the single value decomposition to compute the pseudo-inverse. In our algorithm, we try to avoid that. First, I want to explain a fast algorithm to compute the pseudo-inverse. The classical method to compute the pseudo-inverse is given by this formula, and for that we need to compute the single value decomposition for matrix set. A fast algorithm to compute the pseudo-inverse is given by two formulas, and the first formula depends of the rank of matrix set. If the matrix set is a full rank, we use this formula. If the matrix set is a rank deficient matrix, we use this other formula. Both formulas are similar. The big difference is here because if set is rank deficient, this product of matrices is singular, and we cannot compute the inverse. For that, we use a regularization with this matrix. In this case, this is a diagonal matrix, and alpha is a positive number close to 0. In this example, we try to compare the execution time of both methods, of the classical method and the TPN method. We present this diagram choosing different values of dimension f, and we can see the big difference between the fast method, the TPN method, and the classical method, and the error in both methods is almost 0. The second fast algorithm is to compute the low rank approximation of a matrix. In this case, the classical method using the SVD is given by this formula. We use other technique based on a bilateral random projection. In this case, we need to use two random matrices, A1 and A2, to create a bilateral random projection Y1 and Y2, and the formula is given by this one. When we try to compute the execution time using this formula and this formula, there is no big difference in the execution time. For that, we try to simplify this formula using a particular choice of matrix A2. And this new formula is called the modified bilateral random projection method. And for that, we need to choose a matrix A2 using this particular formula. If we use this particular formula, we can simplify this formula in this one. And here we just need to compute one pseudo-inverse. And if you can note, we can use the TPN method to compute the pseudo-inverse of this matrix. We compare the classical method to this new formula, the execution time, and we can see the big difference. And the proposed method is faster than the classical method, and the error of both methods are almost the same. Now, the proposed method to clean a image for image deconvolution, the first step is we need to to obtain the training data to create the matrices capital X and capital C. After that, we compute the estimation of the pseudo-inverse using the TPM method. After that, we create the kernel matrix given by this formula and compute the low rank approximation using the MBRP method. And finally, compute the matrix that clean the image with noise. We apply this algorithm using 2,000 different satellite images from the NASA Solar System Exploration database. For that, we want to clean this image using a database. Also, we create a training noisy image using this model. In this case, A and N are created using a normal distribution. And here we have some examples of the training data. The first row represents the image without noise, and the second row represents the image with noise. We applied the classical method and the fast method to reconstruct this image with noise. We don't know this image. This is the image without noise. We just know this image with noise, and we have the reconstruction using the classical method. And here we have the reconstruction using the fast method. We use different values of R, of compressed region, to reconstruct the image. In both cases, the results are almost the same. In this table, we can see numerically the results. The error are in both methods is the same. However, the time execution is
sorry
different.
for the. You just have 2-3 minutes left.
Sorry?
You just have 2 to 3 minutes left.
Okay, sorry. Yeah, I'm finished. Sorry. And if you see, the proposed method is faster. And finally, in this presentation, we propose a new and faster method for image deconvolution based on the RC problem. And this new method is based off a tensor product and Tikhonov regularization to approximate the pseudo-inverse, and bilateral random projection to estimate the low rank approximation. And the numerical results that we obtain, we see the advantage of the proposed method. Finally, we obtain 2 theoretical results over the error analysis of both techniques. Thank you so much.
Thank you for your presentation. Any questions? Okay, then we move on to Dr. Oguzhan Kornaz presenting multi-image crowd accounting using multi-column.
Hello, dear participants. Can you hear me?
Yes, we can.
I'm sharing my presentation, but I cannot. I'm waiting. Can you see the presentation?
No. Yes, now we can see it.
Yes. Again, hello, dear participants. My name is Oguzhan Kornaz. I am research assistant at Bursa Technical University in Turkey. Today, I'm going to talking about our study that we prepared with my advisor, Associate Professor Cemal Hanilci. Let's look at details of this study. In this presentation, we will talk about these outlines. What is the crowd density estimation? How can we contribute to this topic? And what did we do? What is the pre-process of our proposed method? Where did we inspire? This means what is the baseline study of this topic? What did we propose it? What is the process of our method? And what did we obtain and results? Problem definition. Crowd is a unique group of individuals. Something involves community or society. Crowd counting or density estimation is an important problem in crowd analysis. Crowd density estimation could be used to measure the comfort level in public areas or to estimate crowd density using either still image or video sequence. Contribution of this paper, rather than training each convolutional neural network named as CNN with the same input image, we propose to use different preprocessed versions of the input image with each CNN. Rather than using multi-column CNNs in an end-to-end type as proposed in MCNN paper, we propose to use it for feature extraction. We use support vector regression SVR using the feature extracted from MCCNN for crowd density estimation. And last one, a slight modification on previously proposed MCNN is introduced, and we compare its performance with the proposed technique. Methods. Preprocessing method, region of interest, named as ROI selection. On crowd density estimation, the region is in which no one appears do not contain useful information. Thus, using only the regions in which people appear, referred as region of interest or ROI, in the images considerably improves the crowd density estimation performance. Therefore, we first apply selection of ROI as a pre-processing step to the image. To do so, relevant regions in the image are first determined, and then the pixel values is remaining regions are set to 0. You can see the equation. In this equation, if the pixel value that is located XY location in image plane is not element of ROI, so this pixel value is set to 0. Methods pre-processing, perspective normalization. Previous studies in crowd density estimation show that camera position has an important effect on the performance. Since people closer to the camera look greater than further away, perspective normalization (PN) should be applied as a pre-processing step to the image for reducing the adverse effects induced by the perspective. You can see this picture, A, B, and C image. In these pictures, H1 and H2 is same person, but the pixel counts of H1 and H2 is not equal because of camera perspective. Therefore, we weighted the pixels from AB line to DC line with H1 divided by H2 coefficient. Baseline. Single image multi-column convolutional neural network named as MCNN. Since multi-column convolutional neural network MCNN was originally proposed for crowd density map estimation and reported a great success, we implemented a slightly modified version of MCNN for comparison. The structure of modified MCNN for crowd counting is depicted in figure 2. In the original MCNN approach, each column consists of 4 convolutional layers with different number of filters and different kernel size. The output of the last convolutional layer from each column was then merged to form a feature map. Finally, a convolutional layer with 1x1 kernel was used to convert a feature map to density map. You can see figure 2. In this figure, 20, 24, and 16 are the filter numbers, and 7, 5, and 9 are the filter size of convolutional layers. The inputs of this model are original unpreprocessed images. Proposed method. Our proposed method is a multi-image, multi-column convolutional neural network. Difference between MCNN and MCCNN is multi-image or single image. Feature extraction multi-image, multi-column convolutional neural network. In this study, we propose to extract features using multi-image, multi-column CNN, named as MCCNN, to count crowd. The overall structure of the proposed MCCNN and the number of parameters in each convolutional and fully connected blocks are shown in figure 1. Concretely, MCCNN is a deep neural network consisting of 3 CNNs in parallel. You can see figure 1. In this figure, 256, 128, and 64 are the filter numbers. You can see here, here, and here, and here are the filter numbers, and 5, 3, and 2 are the filter size of convolutional layers. The inputs of this model are different from each other. The first column's inputs are original images. The second column's inputs are foreground images of original images, and the third column's inputs are age detection applied image to original image. Subcases of MCCNN method. In order to analyze the proposed MCCNN approach and to provide a deeper analysis, we consider 5 subcases in experiments. MCCNN1, crowd counting is performed in an end-to-end fashion using only first column of MCCNN structure. MCCNN2, similar to MCCNN1, but the second column of the MCCNN architecture is used for crowd counting. MCCNN3, similar to MCCNN1 and 2, but the third column of MCCNN is used. MCCNN4 is different 1, 2, and 3 from 1, 2, and 3. MCCNN structure is used for crowd counting in an end-to-end manner. To be more specific, MCCNN is used for both feature extraction and regression tasks. Finally, MCCNN5. MCCNN is used for feature extraction and 60-dimensional feature vector obtained by combining the embeddings extracted from each column is used with SVR, support vector regression, to perform crowd counting. Subcases of MCNN method. Similar to proposed MCCNN, we analyze the performance of MCNN method in 5 different ways. MCNN1, given an input image, the first column of MCNN is used in an end-to-end fashion for crowd counting. MCNN2, similar to MCNN1, but the second column of the MCNN is used. MCNN3, similar to the MCNN1 and MCNN2, but the third column of the MCNN is used. MCNN4 is rather than different from 1, 2, and 3. Rather than using MCNN for feature extraction, end-to-end crowd counting is performed using the modified MCNN. Last one, MCNN5. MCNN5 features extracted from each column of the MCNN are combined into a single feature vector, and then SVR, support vector regression, is used for regression. Experiment, we used metrics mean absolute error and mean square error as a metrics, performance metrics. The dataset, we used dataset, USCD dataset, contain 2,000 images, 1,280 images for training, 320 images for validation, and 400 images for test. Last one, optimizer and learning rate. Adam optimizer is used for optimizing the parameters of the network with 0.0001 learning rate. Results, you can see the results in table 1 and table 2. Table 1, crowd counting results using MCCNN and modified MCNN. The best number in each row are given in boldface, and globally best numbers are shown in boldface and underlined. Table 2, comparison of the proposed method with previous studies on UCSD dataset. Thanks for your attention.
Thank you for your presentation. Any questions? Okay. Now we move forward to Mr. Timothy Scott Shu, who will present performance analysis of a neuro-fuzzy algorithm in a human-centered and non-invasive BCI. Mr. Timothy, the floor is yours.
Thank you very much. Can you see my screen?
Yes, we can.
Good day, everyone. I hope all of you are doing well. So my name is Timothy Chu, and I'm going to be presenting my paper, the performance analysis of a neuro-fuzzy algorithm in a human-centered and non-invasive. This is actually a portion of my dissertation under the mentorship of Dr. Alvin Chua and Dr. Manuel Seco. So a brief background on the topic is BCI stands for brain-computer interface. It's worth noting this term because I will be frequently mentioning this. So As the name suggests, we focus primarily on the brainwave activities. So this would mean we gather and translate this data information and apply them into different implementations, whether it can be robotic applications or, I mean, we could use the BCI to control or maneuver robots or unmanned vehicles such as drones to conduct probably medical or geological mapping implementations. So my primary motivation was that I know some senior citizens who are still very much capable of working and would still like to work, or some senior citizens who would want to continue their hobbies, a woodworking, something like that. So with that, I was hoping to give them that possibility with the use of PCI robotic applications. So how does this work exactly? So the brain interacts with different parts of the body by sending electrical signals through the nerves and synapses to the desired limbs. So, and then the main function of BCI machines is to capture these electrical signals through a test called electroencephalogram, or EEG for short. So BCI machines can be invasive or non-invasive. When we say invasive, it just means that surgical operations are required to embed these machines in a person's body. Non-invasive, on the other hand, simply implies that we strategically position these sensors along the brain, or I mean along the head. Okay. So this is how information is obtained. Then they are sent to the computing hardware, where they will be processed and used for a desired implementation. Currently, there are already some BCI robotic implementations, mainly the a robotic arm implementation. And these studies mainly vary in the machine learning algorithm that they employ. So this is what I wanted to explore. So convolutional and artificial neural networks are one of the most common or popular algorithms being used for this implementation. However, when managing massive datasets, they tend to take up large computational resources. Another popular algorithm is the support vector machines. Though they are very efficient and can effectively classify signals, provided that a user is able to design or use a proper kernel for whatever reason whatever use case they have. And sometimes it can be challenging for them especially when they are required to design a special kernel for their special use case. Now, in the study by Li and Feng 2019, they noticed that similar gestures, for example, I'm moving my left arm and my right arm, both of these actions showed similar brainwave patterns, consequently having a degree of overlap in EEG dataset. So this phenomenon actually affected the performance of the machine learning algorithms. So the challenge now is to utilize or develop an algorithm that offers good accuracy and can adapt to this phenomenon. So for this research, we employed the Adaptive Neural Fuzzy Inference System, or ANSYS for short. And it's an algorithm that was conceptualized and developed by Ji-Xing Roger Chang in 1993. So in a nutshell, it's a fuzzy inference system and adaptive network combined. It's composed of 5 layers, where the first and the final layers handles the fuzzification and the defuzzification process. The hidden layers is then where the weights and biases are being adjusted, similar to how an adaptive network adjusts weight and biases. So here you can see on the top is our overall architecture and methodology system. And on the lower left, you could see that I use face gestures as my EEG data generation technique. So by doing face gestures, this actually activates the frontal lobe of the brain, and it generates appropriate EEG signals according to whatever face gesture you're doing. So on the top part of the face gestures, I use neutral, smile, shock, and clench. However, you also notice that I'm on the bottom, I have another set of face gestures, which focuses on the eye movements. So these actions also have the same phenomenon as explained with the face gestures, wherein they produce electrical signals through the frontal lobe of the brain. It is also worth noting that these EEG signals, when they are captured by the BCI machine, they are measured in millivolts. So once that the EEG signals are generated, I use the emotive insight as my BCI machine to collect the data. Here on the lower left section of the slide, we see the sensor or electrode layout of the emotive insight. And for this technique of EEG data generation, we are very interested or primarily interested in the two sensors on top, AF3 and AF4, since they are the ones situated at the frontal lobe. Initially, I gathered EEG data with face gestures and tried to utilize it without using any pre-processing techniques, which served as my first EEG data. As you can see here, it's the raw data. However, when I tried to process it, I got results that were not very satisfactory because the data set was too noisy and actually it was quite large. So then I proceeded to get another set of data, which is the eye gestures. And then I applied pre-processing techniques such as the Butterworth bandpass filters and heuristic filtering. Butterworth bandpass filters are just supplementary concept to bandpass filters that utilize pass bands and stop bands. In other words, we're employing a cut-off frequency to manage which brainwave signals will be obtained and fed into the system and which signals will be blocked. Heuristic filtering, on the other hand, is where I plot the obtained values against time and manually locate the minimum and maximum peaks. The reason why I did this is that these peaks actually can sufficiently define a particular gesture. So the expected data set should have a multiple of 5 features. Now, why is it 5? Simply because I have 5 sensors or 5 electrodes in the emotive insight. Now, why did I say multiples? Because I took the data in various sample counts, as shown here in the specifications below the emotive sensor layout figure. So a sample count refers to the number of data samples being retrieved in intervals of 10 milliseconds. And these would be all taken under one epoch. So one sample will provide me a row of 5 features or 5 values, which are obtained through the 5 sensors. 2 sample counts will give me a sample of 5 features or values and another set of 5 values taken after 10 milliseconds. And consequently, 4 sample counts would give me a data of 20 features or 20 values in one row. So after that, I ended up getting these sets of data sets. So as you can see, my first 3 rows are the data used from face gestures, while the remaining 2 is from the eye gestures. As you can see, I have a relatively large data for the first with the face gestures, with having 800 rows of input, while the eye gestures have around only 250 rows of input. So my approach was to analyze the performance of the ANFIS against a known algorithm, which is the SVM, to put the performance of ANFIS into perspective. So the figure on top shows the average accuracy results for all algorithms when managing this particular EEG dataset. I also placed the face gestures I use on the bottom right of this slide, just for your reference. So the green bar represents the accuracy ratings of the SVM, while the yellow represents the ANFIS in 5 epochs, and orange is ANFIS of 10 epochs. So in one sample count, 5 features, ANFIS was able to perform comparably well with SVM, with accuracy ratings of 63% for 5 epochs and 57.58% for 10 epochs, while the SVM got 57.91 epochs. So, and then as I increased the features of my dataset, the SVM was observed to perform better by getting accuracy ratings of 85 and 82% for 2 and 4 sample counts respectively. However,
We still have 2 minutes.
Okay.
Okay.
However, you can notice that ANFIS was unable to generate any results for 2 and 4 sample counts because I received a memory error, meaning it just ran out of RAM. Then on the table below, you can see that SVM on the third column just took a fraction of a second to be trained and create predictions of it, while ANFIS on 5 epochs took 17 seconds, which is nearly 5 hours. So, and then on the second data set, as you can see, ANFIS was able to perform better in the sense that I have now results for the 2 sample count. And generally, the ANFIS was able to perform comparably with SVM or even better to some degree. So I'll just focus on the 2 sample counts because of the time. So on 2 sample counts, the SVM performed 80%, while the ANFIS performed around 89 to 90%. Very good for this case. And then in the training time below, table below, it shows that again SVM was trained only with a fraction of a second, while ANFIS took considerable time. Like for 2 sample counts, 48,000 is nearly 13 hours. So this research explored the applicability of the neurofuzzy inferred system by conducting a performance analysis of ANFIS against SVM in EEG data classification. The research employed the use of facial gestures to generate EEG signals and being retrieved by the emotive insight. So overall results show that the ANFIS offered comparable or even better performance in SVM in terms of accuracy. However, the algorithm experienced limitations when managing large data sets. It was noted in the study by Jankani, 2008, that ANFIS can perform actually efficiently with 6 features. So this concludes that ANFIS is actually a viable algorithm for BCI implementations, as its accuracy ratings are comparable to the SVM, and it only requires a relatively small data set. And so researchers recommend that a direct interface with the neuro headset and the algorithm, because in this research we employed the OpenVibe. It was found to be a bit clunky, so a direct interface might be better. And the research findings are open to other methodologies where intuitiveness of the interfaces can support the end user while interacting with the machine interface. Thank you very much for listening to my presentation. I'm open for any questions.
Thank you for a great presentation. Any questions? Okay, we move on then to Dr. Hiroshi Tozono, who will present the visualization system of image search space on convolutional spherical self-organizing map implemented using WebGL. Dr. Hiroshi, the floor is yours.
Can you hear me?
Yes.
Okay. Oh, I must want to leave meeting because the PowerPoint cannot be shared. So I will come back soon.
Okay, no problem. Okay, then. Then we go to Dr. Muhammad Hanif, will present an improvement in multi-query person re-identification using cumulative distance aggregation. Dr. Muhammad, the floor is yours.
Yes, give me a minute, please.
Yes, we can hear you.
Okay, I'm back.
Okay, Dr. Muhammad will present now, and Dr. Hiroshi will. Okay. Dr. Muhammad, so I'm sorry, just after Dr. Hiroshi finishes his presentation.
Yeah, I can wait.
Okay. Dr. Hiroshi, we can't hear you.
I see.
Okay.
Okay. The title of my talk is the visualization system of image search based on convolutional spectral self-organized map implemented using WebGL. This is a group work of these members, and it is mainly done by Kenta Toizumi when he was in master course student, and he had been employed by Fujitsu. Okay. Recently, deep learning is applied to many areas. For example, image processing, natural language analysis, big data analysis, and internet search. And it shows incredible performance in many applications. However, huge number of training data is required for deep learning, and the computational cost of training is very high. So special hardware such as GPU is required. On the other hand, for some tasks, deep learning may be excessive. So simple neural network will be suitable. For example, self-organized map, as for the self-organized map, it uses a single layer neural network, and it performs unsupervised clustering, and it uses simple learning algorithm. So the purpose of this research is development of the system based on spherical sum, which can be visualized the relation among the images searched from web. At first, I will speak about the implement of spherical sum. This is the agenda of this part. Sum is a kind of neural network which was proposed by Kohone and can be can extract the future on the multidimensional input vectors and can visualize the relations among them by supervised and unsupervised learning. And some can integrate multimodal input vectors and can extract relations among them on two-dimensional plane. This figure shows the learning algorithm of sum. At first, the map layer is initialized in random. And if the input data is given, the winner neuron, which is most similar to the input vector, is selected. And the winner neuron and its neighbors are updated. And for second data, and for third data. And by repeating this 50 steps, this map is organized. This is a famous example of sum, which is the clustering of the animals. Each animal is represented by a future vector, and the element of the each element of the future vector denotes the properties of the property of the animal, such as small, middle, and big, and so on. And using these vectors as input vector, this map is organized. And after the map is organized, the animals are mapped. Then the similar animals are clustered closely on the map, and the similar animal is mapped far from the animal. However, the conventional sum have a problem, and number of neighbors neurons is different depending on the position of the winner neuron. When the winner neuron is in the center, there are many neighbors. However, when the winner neuron is the edge of the map, it has smaller neighbor neurons. And secondly, winner neurons are tended to be mapped at edge on the map when the map is trained well. On this map, many animals are mapped on the edge of the map. For this problem, spherical sum is proposed. In spherical sum, problematic edges are eliminated by mapping the neurons on the surface of the sphere. As a commercial spherical sum, Blossom is developed by SOM Japan. However, this system is implemented using API of Windows, so it cannot be executed on another OS. However, recently many types of devices are used, like PC, tablets, smartphones, and many OSs. So we implement the spherical sum using WebGL. Using WebGL, it becomes to display 3D graphics such as sphere in web browser. It becomes also possible to implement GUI which can manipulate such a rotate and zoom the sphere. The program can be written in JavaScript. And for making sphere for making a sphere, we use the hexahedron. To map the neuron uniformly on the sphere, hexahedron, which is the largest polyhedron, is divided repeatedly, as in figure. And division of hexahedron is done as follows. And the new neuron is generated in the center of the edge of the triangle. So number of the neuron after n division is calculated in this equation. This figure shows an example of spherical sum using animal data. Compared with the previous map, the animals are mapped uniformly on the sphere. Next, I'll speak about the clustering of images using spherical sum. The agenda of this part is as follows. For image search of Yahoo and Google, the resulting images are displayed in order of the number of the accesses and page ranking or keywords. In our method, clustering of image using spherical sum, the images searched from the internet are clustered using spherical sum to visualize a relation of them based on similarities. At first, the images are acquired. Using Python package, Google Image Download, images can be searched with keyword and can be downloaded from internet. And for convolution, original image is divided using sliding window, and the correlation coefficient is calculated between each filter and divided images. In this experiment, we use these filters, and perform max pooling. We taking the maximum value of each correlation coefficient in sub-region, and using max pooling, the shift invariance is obtained, and it needs lower computational costs. After that, clustering using sum is performed. The convoluted and max field value of correlation coefficient is used as input vector for each image and given to spherical sum as training data. After training, each image is displayed as the winner neuron of input vector on spherical sum. So next, I will show an example of a clustering experiment. As the first experiment, we acquire the images using Google Image Download, and search keyword is set as natural. And we use this very old type computer, and program language is JavaScript plus WebGL. This figure shows the results. The similar images are clustered closely on the map, and the sphere can be manipulated using the mouse or fingers on the tablet. And by clicking an image, the original image is displayed. Next, I will show another example of the clustering. In this case, we use the keyword sunset and sea. This is the result.
You still
As
have
same
2
as the previous
minutes.
figure, 2 minutes.
2 minutes, yes.
Okay. The images are clustered well on the surface. And to confirm the effect of the changing filters, double filters are used. Double filters are generated from kernel by localizing sine cosine functions. And we use this type double filter. This figure shows the results, and the left figure is a previous result, and the right figure is a result using double filter. The clustering results becomes a little better than previous one. And I will skip this. And as experiment for numerical evaluation of accuracy, C-pattern image clarification is conducted. In this experiment, 2D convolutional sum was used because our spectral sum cannot classify the supervised input data yet. The experiment setting is as follows. And this is the result. Using larger map, the accuracy becomes very good. And this is a resulting map for 64 by 64 size. For overall the map, the images are clustered according to the color. And on the magnified map, the images are clustered based on the contents. Conclusion, the visualization system of such image based on convolutional zero-order map is developed. And in implementable system, WebGL is used for compatibility to various devices. As the future work, evaluation of the system by many users is required. And every evaluation of the clarification accuracy and improvements are required using spherical sum. Thank you.
Thank you for your presentation. Any questions? Okay. Then we move on to Dr. Muhammad Hanif will present an improvement in multi-query person re-identification using cumulative distance aggregation. Dr. Muhammad, the floor is yours. Dr. Muhammad. It seems Dr. Muhammad is not with us. Dr. Muhammad?
Hiroshi?
Okay. He's joining the room now.
Yes, yes.
Dr. Muhammad?
He's online, I think. He's connecting.
Yeah. Dr. Muhammad, can you hear
Hello.
me?
Yeah, I can hear you. Can you hear me?
Yes, yes. The floor is yours to present your presentation.
Okay, thank you.
Yes.
Let me share my
Muhammad
screen.
Hani's presentation, right?
Yeah.
So you're done with the presentation, right?
Yeah, yeah.
Yeah. So, any questions, sir?
Oh,
Okay. So,
I'm trying to start making some technical
you,
difficulty.
yeah.
Can you see
No
me?
problem, sir. Thank you. Thank you for your
Yeah.
presentation. Yes, yes, yes. Do you want to conclude with your remarks?
No, he's just presenting now. He will start his presentation.
Okay.
Can you see my screen?
Yes, we can. Yes,
Yeah.
we can.
Thank you. I'm presenting the paper ID 545, an improvement in multi-query person re-identification using cumulative distance aggregation. So my name is Mohammad Hanif. This is the table of content, and I'm starting with the introduction of person re-identification. The aim of person re-identification is to find the query or person of interest from the gallery or
So
network.
sorry to interrupt. You can start from where you have stopped, sir. Excuse me.
Yeah.
So
Sorry.
you can begin from where the presentation was stopped.
I'm starting from now.
Begin from where the presentation was stopped, sir.
He's just started. Now
Again
it's
from the
just
beginning, sir.
Yeah,
Yeah.
I'm just starting now. I haven't presented
Yes, sir.
before. Okay, so the person identification is mainly
Okay,
treated as
okay.
the image retrieval problem. So it has various applications in security, surveillance, tracking, image retrieval, video analysis, or crowdsourcing, etc. And person identification, there are many challenges faced in person identification, which minimize the accuracy of the system, such as occlusion, body parts missing, illumination variations, misalignment, scale variation, and viewpoints variation, etc. So the critical inconsistency in the intra-class and critical similarity in the inter-class images makes the biggest problem in person re-identification. While the different people's looks like same due to the similar clothes or luggages, etc., or the same person looks very different in the different cameras view due to the change in background or illumination variations. So to identify a person in network of cameras is a difficult task. Here are some visual challenges in the image. You can show the A part shows the hidden occlusion, and B part shows the body parts missing, and C part the illumination variations. D part shows the misalignment, scale variation, and viewpoints variation are seen in the image as a challenges of person identification. And here we can see the interclass inconsistency in the top row of image and the and the similarity of different classes in the bottom row of the image. So the multi-query person identification, it consists of more than one images to combine their features or their benefits to recognize an image in the network of cameras. So multi-query is the best of is the most effective and popular ways. There are two main methods, the multi-query and the re-ranking. So I am focusing on the multi-query person re-identifications. So traditional methods perform the feature pooling, that is the mean, maximum, or minimum pooling for the person re-identification. Here we are proposing based on this cumulative distance aggregation. So our proposed method is to based on the two hypotheses. The first one is different query images of the same class may have non-identical hard negatives and the non-identical hard positives. And the by cumulative distance of multi-query, the non-identical hard negatives are repelled and the hard positives are pulled in the rank images. So it increases the accuracy of person re-identification. So here we can really see that the probe images first, second, and third have the non-identical hard negative and positives, and our proposed method pulls the positive images and repels the negative images to so the system improves better. This is an other example of our proposed methods benefits. So considering the low time, I am moving on. So proposed methodology is based on these steps. First of all, we select the query, then randomly selects an images. Then we calculate the distance of multi-query features with the gallery images. Then the cumulative distance is calculated based on multi-query distance, and then rank image based on the multi-query cumulative distance. Here is the visual representation of our proposed method. We can see the query image, selection of query images, and then distance aggregation from the gallery images. Then the distance is aggregated, and we calculate the final distance of the multi-queries with the gallery image. So the proposed method, we have utilized the Market 1501, CUHK03, Duke, MTMC, and mass data sets for the results comparison. And our evaluation matrices are the mean average precision and the cumulative matching characteristics rank 1 score. So for the baseline, we use the ResNet 50 convolutional neural networks pre-trained on the ImageNet data sets, and with the SGD optimizer and soft max loss learning rate with 0.1, and which is updated after every 40 steps. So there the results, we just presented the results of feature pooling, where the mean pooling approximately performs better in the almost all data sets. Here is our proposed method results based on distance aggregation, and we can see the max mean performs better than the mean distance aggregation. So here is the comparison of both cumulative. In previous two tables, we selected the best feature pooling and the best cumulative distance, and here we compared the results of cumulative and feature pooling best methods, and we can see the cumulative distance perform in almost all data sets, both in rank 1 accuracy and mean average precision significantly. So here we evaluate our parameter like the number of queries used as the multi-query. So if we used only one image as a query, the accuracy is like about 84. And if we utilize the more queries, so the number of queries are 3 or 4. So as we increase the number of queries, the results improves gradually. But the major gap is between single image and the 2 queries images. So as it combines the effect of both. So conclusion, it is verified that multi-query percentage identification performs better than single query. Then we evaluated the results of traditional feature pooling and proposed distance aggregation methods. We proved that our proposed multi-query based percentage identification method outperform the traditional feature pooling methods. And in the future, the performance of proposed re-ranking method can be improved by using more strong baseline features and by checking the system of our proposed method on various data sets or large based data sets. So thank you, and ask me if you have any questions. I would like to answer.
Thank you. Thank you for this good presentation. Any questions? Okay. Well, I sincerely thank our authors for their excellent presentations and contributions in this session, and all our participants for being a part of this international congress. I hope this session was informative and knowledgeable as well. All the presenters would be getting their digital certificates through mail within 2 working days. Further, all the papers I have already forwarded to Springer. The publication will be live within 4 to 6 months. Kindly cooperate with the team of ICICT 2021 as and when intimated. Of course, I also want to thank our session chair, Dr. Shamim Kaiser, for chairing this session. A token of appreciation to the chair on behalf of the ICICT 2021 and Global Knowledge Research Foundation. Thank you for your presence. And I kindly
Thank you
I
very much,
kindly
Muhammad Ali.
ask you to turn on your cameras for a quick screenshot for the virtual conference. Okay, thank you. Thank you very much. Stay safe and take care. Well, precaution is better than any cure. Thank you again.